This video is about enthalpy change. Enthalpy change is essentially the change in energy, okay? The change in energy from the reactants to the products, right? In a chemical reaction. And it's denoted by delta H, delta representing change and H representing the energy, right? It's called enthalpy change. Right. When discussing enthalpy change, there are two very important things you need to know. You need to know what an exothermic reaction is and what an endothermic reaction is. Quite simply, exothermic reactions are reactions that give out energy, right? And endothermic reactions take in energy. So, when talking about what makes a reaction exothermic or how you know a reaction is exothermic, there are two ways. One is by knowing the enthalpy change. But if you have to calculate the enthalpy change, how do you do that? Well, when bonds are broken, right, that is an endothermic reaction, right? If you think about, you know, two people holding hands, right? Two people are holding hands. If you want to split the hands, right, you want to make it, you want it to split, you need to put energy. You need to put some force, right? So that is how you can remember bond breaking is endothermic in nature. Right? Bond breaking is endothermic, and therefore, by that logic, bond formation is exothermic. Right? Bond formation gives out energy. Because bond forming, you're putting your hands closer together. Whatever energy was in between your hands, in the space between your hands, it's given out. It goes out. Right? So uh, bond formation is uh, exothermic in nature, energy is given out, and bond breaking is endothermic. Right? This is a key concept to know. Secondly, before and it's the last thing we must know before we look at enthalpy change. It's the activation energy, right? Denoted by E with a lowercase a. This is activation energy, right? It's the minimum amount of energy required for any reaction to happen, right? If it's exothermic or endothermic, it's the amount of energy that any two colliding particles must have to react, because once particles collide, right, for a reaction, they also need to have some energy left over for it to actually form a bond. Otherwise, they'll just collide. So usually we have reaction pathway diagrams which, show this. A reaction pathway diagram essentially represents energy and time, energy levels over the reaction time. So energy is usually denoted by kJ, kilojoules, right? So energy, and you have time, or the progress of the reaction. Okay, so you'll usually have one flat line, something like this, and then there's a small jump, and then it dips, and then it becomes flat again. So here, from this part till here, right, this is your activation energy, while the distance between the bottom line and the top line, that is your enthalpy change. Right? Not the whole thing, only the difference between the reactants and the products. This is important. So this is a representation of an exothermic reaction. Because exothermic reaction, the energy is given out. See, this yellow line represents the energy of particles, not of the surroundings, right? And since it represents the energy of the particles in an exothermic reaction, the energy is given out and it goes to the surroundings. So there is a dip in the energy level of the particle itself because energy can't be made or destroyed, right? It can only be transferred. So if you were to look at a reaction pathway diagram for an endothermic reaction, right? Uh, it look something like this, right? Now, one thing you must notice is that here too there is a dip after there is a peak, and that is because energy is required to form the bonds, and that energy is given out, right, in the endothermic reaction. So that's why there is this dip, the dip in the formation. However, one key thing to note is while delta H remains the same, the enthalpy change it remains the same, right? The difference between the reactants and the products. The activation energy, however, is no longer just this part. It's all the way from the reactants till the tip of the curve, right? Because this much energy is required for the reaction to happen. This is an endothermic. You might be asked to label such reaction pathway diagrams, and in such case, you must also include the product and the reactants. You must also label the products and the reactants. So look at reaction pathway diagrams and activation energy. Now, when we look at actually calculating enthalpy change, we need a reaction, right? A reaction, any general reaction is fine. All right, let's look at combustion reaction first. So combustion is always exothermic, and yeah, combustion is always exothermic. That's something we need to remember. So now let's look at a reaction. Let's take the combustion of methane. That's CH4. So more often than not, you're going to get a reaction in the symbol form, and you will be asked to balance it and then work out the enthalpy change. Right? So let's write our reaction, the skeleton reaction. It's CH4 plus O2, and you're going to have CO2 and H2O as your products. A classic combustion reaction. Now, when we look at balancing this, you're going to have 2H2, 4, and 2O2. That's balanced. Now, when we are looking at enthalpy change, we also have to look at the how the molecule bonds, the bonds between the atoms in the molecule. So you might have to figure this out on yourself, or you might have it given to you. So methane looks something like this, a carbon with a single hydrogen bond on all sides. And oxygen is a double bond. So oxygen's a double bond. Carbon, again, it's a double bond between oxygen and carbon. And H2O is two single bonds. Okay. Just for the sake of understanding, I will draw all the atoms. So now that we have this here, usually you won't have the second molecule given. You will only have the first molecule as in the structure, and then you have to multiply. So we said that enthalpy change was uh, the change in the energy, right? Change in energy. So first let's calculate the total amount of energy in each molecule. So how we're going to do that is you will be given a table with the compound, another compound here, CH4, O2, etc. And you're going to have some number, right? So you're going to count the number of bonds. That's why it helps to have this as in a diagrammatic representation, so you can easily count the bonds. You're going to count the bonds and multiply the number. And you will be allowed to use a calculator, and usually the numbers can get quite big. So let's look at methane, right? CH4. In methane, we have 1, 2, 3, 4 CH bonds. That's 4 into CH bonds. Now, a CH bond typically has 435 K. It requires 435 kilojoules per mole, right? That's the bond energy. So we're gonna have 4 times 435, and using a calculator, that gives us 1740 kilojoules per mole. Now, considering we only have 1 mole of methane in this reaction, we're going to have 1 times 1740 kilojoules per mole, and this is 1 mole. So you have 1740 kilojoules. Now I'm going to do the same for oxygen. So oxygen is a double bond, in one molecule of O2, this is a double bond. So it's 1 times, the O double bond. And a common mistake that many students make is that when they see O2, they think there are two bonds. No, it's one bond. Remember, a bond involves two atoms, not one, right? So, uh, a no double bond typically has 497 kilojoules. The bond energy is 497 kilojoules per mole, right? And now it's 1 into 497, so it's 497 kilojoules per O2 molecule. Now, since we have 2 moles in this case, right, we have 2 moles here, we're going to multiply it with the number of moles. So we have 2 moles into 497 kilojoules per mole. And the moles will cancel, and that should give you 994 kilojoules. Right? So we have our bond energies for our reactants. Now let's look at the products. Carbon dioxide, it's 2 bonds, 2 CO double bonds, right? 1, 2. So that's 2 into C double O bond. And C double O bond typically has 803 kilojoules, right? So that's 2 into 803. Now we're also going to look at the number of moles, which is just 1. If there's no number, it's just 1. So that's into 1 mole. At 803 kilojoules per mole. And now when we put that through a calculator, we get 1604 kilojoules. Sorry, 1606 kilojoules. 1606. kilojoules, right? And now looking at water, at H2O, we have two OH single bonds. So that's 2 times OH single bonds. Right? So an OH single bond typically has 464 kilojoules per mole, and in our reaction we have 2 moles. That's 2 moles. And now multiplying that, we get 2 into 464 into 2. That's 4 into 464. That should give you 1856 kilojoules. Now that we have all of our individual, you know, compounds, bond energies, we're going to have to add them up. So the formula for an enthalpy change is the reactants or the bond energy of the reactants minus the bond energy of the products. And it always remains the same no matter how big the products are, how big the reactants are, right? So our reactants in this reaction is methane and oxygen. That's 1740 plus 994. And our products in this reaction are carbon dioxide and water. So that's 1606 plus 1856. And when we add these up, using our calculator, we get 2734 kilojoules. And here we get 3462 kilojoules. Now that we have our, bond energies for the reactants, let's substitute it in our formula. Delta H is bond energy of the reactants minus the products, and that's 2734 minus 3462, right? And that will give you minus 728 kilojoules. Now notice we got our answer in negative. And we said at the beginning that we're doing a combustion reaction. Combustion reactions are exothermic. So a lot of people get confused here. But again, you must remember that exothermic means that the substance, whatever is undergoing the chemical reaction, that loses energy to the surroundings. Right? It's giving out energy. So we are measuring the energy level of the substance itself. So that's why you get it negative and it's not a positive number, even though you're giving out energy. Right? That's why the number is negative. So once you calculate your enthalpy change, more often than not, you will be asked to identify whether it's an exothermic or an endothermic reaction. If your enthalpy change is positive, then it's an endothermic reaction, and if it is negative, then it is exothermic.